Hi, I'm Kimberly Nicholas. I'm an associate professor of sustainability science at Lund University in Sweden. And I'm going to take you through the Climate Science 101, basically what everybody needs to know about climate change. We can summarize it in almost a haiku if you don't count the syllables too carefully. That is, it's warming, it's us, we're sure, it's bad, we can fix it. These are the conclusions of science that you can read about in thousands of pages of painstakingly compiled and summarized and analyzed synthesis by the IPCC. That's the Intergovernmental Panel on Climate Change. It's world-leading climate scientists who are selected by and appointed by their governments to represent their countries in this international effort that's a major milestone in science. Their latest reports came out in 2021 and 2022, and I'll be summarizing those for you here today and linking with references that you can see on the slides if you want to dive deeper. But the intention here is to give you an overview of what you need to know about climate change so that you have the tools you need to get involved and to help be part of the team working to solve the climate crisis. I'll start with a little bit of a story about this climate haiku. I first heard it's warming, it's us, we're sure, it's bad, we can fix it, in a memorial honoring Steve Schneider, who was my undergraduate thesis advisor at Stanford. He passed away in 2010. And at his memorial service, I heard John Krosnick say these words. They really resonated with me. And I used them to organize my teaching starting that year and the following year. And in 2014, I put these words on my first ever protest sign. I went to my first climate protest back in 2014, organized by some of my students in the Lund University Master's Program in Environmental Studies and Sustainability Science, LUMIS. You can see some of those students here in our bike protest. So I thought, I'm a scientist, I'm not an activist. What goes on a protest sign? Okay, I can actually stand for the science and put footnotes to reference the sources for these claims. So I did that in 2014. I did it again in 2016 at a rally called Stand Up for Science. And there, a smaller version of that footnoted protest sign spread widely when Bill McKibben retweeted it and said, when scientists protest, their placards have footnotes. So here I'll be taking you through some of the evidence and the footnotes behind these claims so that you know where to go for more information. I want to mention that I've also turned this framework into a teaching curriculum based on the IPCC, the synthesis science. And this includes step one that's not part of the IPCC's work, which is It's Climate, which we found with a team of LUMA students analyzing what's being taught in climate courses around the world. They start, many of them, with basic physical definitions and explanations that the IPCC kind of takes as a starting point because they're synthesizing the latest science and not, for example, defining basic terms in climate and energy balance and so on. But those things can be important in a basic course on climate. We won't go into those here because we'll focus on It's Warming and the rest of them forward. But here's just a brief overview and summary of what it looks like to be climate literate, which is how I define being able to read and understand the summaries for policymakers from the IPCC. So if you want to get more into that, I have more information on my website. But let's get started in taking you through a whirlwind tour of Climate Science 101, the basics. First of all, it's warming. These first 3 points come from Working Group 1 of the IPCC. That's the group who focuses on the physical science basis. What do we know about the physical climate? How do we know it? So in talking about warming, how do we know that it's warming? Well, we have observations, measurements from the last several hundred years, dating back to 1659 in the case of thermometers, spreading and becoming continental by 1950 or so, and becoming more global, including the poles, since the 1940s. We still have gaps in density of measurements of temperature around the world. So fortunately, for the last 45 almost years, we've had global satellite measurements that give us a really good global picture. We also have buoys around the world, a network of ocean stations that measure temperature and other physical parameters of the ocean, salinity, for example, and that helps us get a global picture of the state of the oceans. For going back further than a few hundred years, where we don't have direct observations and we can't build a time machine to make direct observations, what we can do to study the climate is look at proxies. A proxy is something that stands in and represents something else. So in the case of climate proxies are, for example, ice cores that are pulled up from Antarctica and contain fossil air bubbles that are a snapshot of what the past climate was like, how much oxygen, how much CO2 was in the atmosphere at that time. Scientists can take cores of lake beds that trap pollen in mud and learn what kind of plants and trees were growing in the area at that time. And that tells us a lot about what the climate conditions were like. Some living things like corals and trees record the climate in their bodies. So in their growth rings, we can see what kind of climate was experienced, what kind of stress, how long the growing season was, how wet or dry it was. So we have many tools at our disposal to help us reconstruct and study past climates. And these measurements and observations and proxies going back in time paint a really coherent picture that it is warming. It's visualized here really elegantly by Ed Hawkins' warming stripes. But if we go into what the IPCC tells us, we know that CO2 concentration, the main greenhouse gas that traps heat near the Earth's surface and is responsible for most global warming, is now at its highest in at least the last 2 million years. Really, really long time. Sea level is rising at the fastest rate in at least 3,000 years. Arctic sea ice is at its lowest area in at least 1,000 years. And glaciers are retreating at the fastest rate and the most widespread in at least 2,000 years. So the warming we're experiencing is unusual. It's happening rapidly, and we see it in many different ways around the world. Altogether, we see warming in the air, in ice, on land, and in the oceans. So together, these observed changes that we can see with our eyes and measure with instruments unequivocally tell us that the world is warming. We know that water vapor and surface temperature and air temperature near their surface are increasing. Those are signs of warming. Ice and permafrost are melting and shrinking, also signs of warming. On land, we have species moving around to try and hold on to their ecological niche. So for example, moving up mountains to try and be in the same temperature as the world warms. Growing seasons are getting longer in many cases. That might sound like a good thing, but it can lead to mismatches between, for example, pollinators hatching or being around, and when plants are blooming. Harvest dates for grapes have been getting earlier, and that can be stressful and also difficult to achieve the optimal ripeness and quality that growers are going for. We see also in the ocean that the heat content of the ocean has increased greatly. Actually, most of the heat that has come from human-caused climate change has gone into the ocean so far. We see sea level rising largely as a result of thermal expansion, that water expands when it's warmer, and that makes sea level rise. Also as a result of ice melting on land and that volume of water being added to the oceans. And ocean species, marine species, are changing their range too. And we see ocean acidification. That's the process where carbon dioxide dissolves in the ocean and it acts as an acid. It makes it more difficult for creatures that build their shells out of calcium carbonate, which is basic, to make a living. The writer Elizabeth Colbert describes it as if you're trying to build your home with bricks and someone keeps stealing your bricks. Some of these changes have been really dramatic. There are lots of pictures available from research online showing melting ice and glaciers, like this site from Alaska that compares in the late 1800s, this really widespread ice field, and more recently, an enormous melt and receding of ice and glaciers. And we see changes in the global water cycle across the atmosphere, ocean, and land, and in polar and frozen regions. So with warmer temperatures, the air can hold more water. And that means there's more and faster evaporation and heavier precipitation. So basically, climate change and warming is speeding up and amplifying the global water cycle. And we get both, seemingly paradoxically, heavier rainfalls and intensifying dry seasons and droughts as a result. Here's another visualization from Ed Hawkins. Oops, sorry. There we go. Showing global temperature change from the beginning of a strong instrumental record till recent days. And we see how rapidly we are accelerating warming and how fast we're getting close to this limit of 1.5 degrees C of warming. These red lines are what's set in global climate policy, most recently in the Paris Agreement, to avoid dangerous climate change and to limit global warming to well below 2 degrees and pursue efforts for 1.5. We know from the latest science that it's so critical that we get as close as possible to 1.5, that we stop global warming as fast as possible, because so much depends on that. So we'll look a little more at that in a minute. Okay, we've seen that it's warming. The Earth has warmed and cooled in the past throughout geologic history before humans were a part of the planet. So what's different this time? How do we know that it's humans causing the current warming? Well, we have multiple lines of evidence that show that humans are driving recent climate change. And I'll show you some of those here. But as an overview, for example, we know that climate models, these computer simulators that are built to help us represent the climate, since we only have one Earth, we can't run controlled experiments on Earth. We have a sample size of 1. So right now, humans are running an uncontrolled experiment on planet Earth, on our one sample of a livable planet that we know of in the entire universe. And in order to study different outcomes, both in the past and in the future, climate models are really helpful. They've gotten extremely accurate and do a really good job of representing many of the big main features of the world's climate. They can't do that if they only include natural forcings, natural drivers like variations in the sun's output or volcanoes. We have to include the human fingerprint to explain the climate that we're experiencing and living in now. We also see that the patterns of warming, like where on the surface it's warming and how high and where in the atmosphere it's warming, is what we expect from physics based on humans burning fossil fuels and trapping heat near the Earth's surface. And also the rate of warming we can see is really different than what's happened in the past. So as a couple of examples, and I encourage you to check out the linked references here if you want to dive more into detail. But basically, when we look at the pattern of observed surface warming, so historically over the last decades, we see that it's stronger over the Arctic, so stronger at high latitudes and stronger over land than oceans. And these are consistent with what physics would predict for warming caused by greenhouse gas emissions. We also see the pattern of vertical warming in the atmosphere matches what physics would predict. That is, it's stronger at the tropics and it's stronger in the lower atmosphere. And we actually see some cooling in the upper atmosphere. That's due to 2 main reasons. One, that the blanket of greenhouse gases that humans are emitting in the lower atmosphere traps heat and prevents some of it from reaching the upper atmosphere. That's one reason for cooling. Another is changes that humans have made to the ozone layer, which thankfully are being repaired and reversed, but at the moment are still contributing to this upper atmosphere cooling. We have some really important chemical evidence that acts as a fingerprint that the carbon in the atmosphere now comes from humans burning fossil fuels. And without going into too much detail, I'll just summarize it by saying that basically taking measurements from different parts of the world show that there's more carbon coming from the global north. The northern hemisphere is where there's most land area and where most burning of fossil fuels happens. Most industrialized countries are located there, and most fossil fuel burning is happening in the north. We also see from isotopes, so different elements that have different numbers of atomic composition that we can detect, show us that the carbon that's coming in the atmosphere is coming from burning ancient plants. And that's what fossil fuels are. Fossil fuels come from primarily plants and swamps that decayed and died, and over millions and millions of years, through geologic time and pressure, became this dense carbon source of fossil fuels like coal, oil, and gas. And those resources are depleted in an aspect of carbon that we can detect in the atmosphere. So fossil carbon is depleted in carbon-13. It preferentially takes up carbon-12. And that matches the signal we see in the atmosphere. We also see that from fossil fuel burning, we know that every molecule of carbon that's burned consumes a fixed amount of oxygen. And we see that change in oxygen also happening in the atmosphere. So we have this unequivocal evidence that the carbon in the atmosphere that's been increasing at about 2 parts per million per year, that's what this second graph here shows, comes from humans burning fossil fuels. And when we take this together, this is the clear evidence that it's us, that current warming comes from human activities. And those human activities are basically, if we look on the left, this is observed warming, the gray, what's actually happened. On the right is the sum of total human influence. And that's primarily greenhouse gases, that second bar. So carbon dioxide and methane from burning fossil fuels, methane and nitrous oxide from changing land use practices and agriculture, and animal livestock agriculture. Then we have a cooling effect from some aspects of particle pollution, so aerosols. And together, if you subtract this blue part from this tall red bar, you get the signal of total human warming, the net warming that humans are causing. And that matches very, very closely with the total warming we've seen. That's different than natural factors or internal variability in the climate. So again, natural factors would be changes in the sun's output or in volcanic activity. Those can change the climate, but they've been very small changes over the period of interest now, and slightly towards the cooling end. So not making a net change in temperature, unlike human activities. And the same with internal variability. The natural range of variability in the climate system can't explain the warming we've seen. It's outside that natural range. We see this here. If we look at it with climate models can only accurately project or reproduce the climate we've actually experienced when human activities are taken into account. So here you need these red greenhouse gases from human activities, and including the blue, subtracting the blue of aerosols. So basically this red minus blue is very close to the observations, the black line. And you see that natural causes have a little bit of variability right around 0, but especially over the last several decades, observed warming has totally separated from, diverged from natural causes. So only including human burning fossil fuels can we reproduce the world that we actually live in, which has been warming rapidly. Okay, so it's warming, it's us. How sure are we that it's us? Well, we are very certain that it's humans causing warming. And this has happened, this has been a process over time. So the most recent IPCC reports were actually the 6th in a line. The first was back in 1990. I show here the second, quote from the second IPCC report back in 1995. And here, regarding the question of how much of warming is due to human activity, humans burning fossil fuels. Back in 1995, the evidence was not as clear. So the conclusion was the balance of evidence suggests a discernible human influence on global climate. That was then upgraded and updated with new evidence in 2001. There is new and stronger evidence that most of the observed warming over the last 50 years is attributable to human activities. That was a big increase. Another big increase in certainty in 2007. Most of the observed increases in globally average temperatures since the mid-20th century are very likely due to the observed increase in anthropogenic emissions. And even more, anthropogenic greenhouse gas concentrations, so human-caused greenhouse gas emissions. The previous IPCC report in 2013, it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. And in IPCC language, extremely likely means a chance greater than 95%. It's extremely certain. Now, the most recent 2021 physical science update made an even stronger conclusion. It is indisputable that human activities are causing climate change. We now have such clear evidence that this is simply a fact, making extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and severe. So this statement coming from the IPCC shows that there's just overwhelming scientific evidence that it's human-caused climate change responsible for the warming we're currently experiencing and many of the negative impacts that it's causing. It's bad. Well, I think we used to talk about climate change, for example, back when I was in an undergrad in the 1990s, and the state of the science was the balance of evidence suggests human impact. We were talking about changes happening in the next century, the one that we're currently living in. And there was less certainty about overall what the impacts would be. People talked more about potential benefits and as well as potential negative consequences. But now we are living in a climate changed world, and many of us, including myself, have personally experienced the harms of human-caused climate change. In my case, my family was evacuated from their home in 2017 due to the California wildfires, which have gotten much bigger and scarier and a longer fire season due to human-caused climate change. The area of land that's burned in the US West has about doubled because of human-caused climate change. So we know that climate change is causing a lot of negative impacts for people and places around the world. And many of these are happening faster than we predicted even a few decades or a short time ago. I think what really helped put climate impacts in context for me was actually this paper, which I read when I was in grad school. It came out in 2007, and it visualized what the oceans look like at different levels of warming. And I think before this, the difference between 1 and 2 degrees of warming, for example, was really abstract for me. It didn't sound like a big difference, but realizing that much of ocean life depends on healthy coral reefs, and coral reefs are extremely sensitive to temperature. And we've seen already in the world today mass die-offs in places like the Great Barrier Reef, where coral experiences bleaching or death because of warming oceans, excuse me, and warming ocean heat waves. Sometimes coral can recover. There's a lot of work going on to try to help make coral more resilient, but we know that coral reefs are among the most sensitive ecosystems, and those that it really depends on. Living in a world with living coral depends on limiting warming to 1.5, because as you can see, a world of 2 degrees warming is a world where we don't have living coral. And a lot of life in the oceans depends on healthy coral reefs. They support a lot of different kinds of animals that play important roles throughout the ocean. They support a lot of commercially important fishing species that are especially important for low-income fisher people around the world. And of course, with more warming, we see more harm. So there's a lot at stake with climate change. We see widespread harm around the world and in different systems from climate change. So extreme heat becoming more frequent and more intense, heavy rainfall as well becoming more frequent and more intense, drought also increasing, causing stress for crops, plants and animals, and human systems, fire weather becoming more frequent, and the ocean warming, acidifying, and losing oxygen, becoming less habitable and less thriving for life. IPCC says, yes, that climate change is causing and will cause unprecedented extremes, that extremes like heat waves and fire weather get larger in magnitude, they happen more often and in new places over a different timing where we might be less prepared for them, and potentially in new combinations that are harder to prepare for and harder to actually cope with. So summarizing, it's bad. Climate change is already bad today. We're seeing harmful effects of climate change around the world with 1.1 degrees of warming that we've already experienced. The more warming we have, the worse it gets. So the goal is to stop warming as fast as possible, because climate is not a linear system. It's not the case that for every, in one way it's linear, which is that basically for every ton of carbon that we burn, we expect a fixed amount of warming. But the part that's nonlinear is the responses to that amount of warming. There can be tipping points where we pass thresholds that are impossible to come back from. And there can be amplifying, escalating effects where a little bit more warming can cause a lot more damage in terms of much heavier precipitation or much greater snow loss and changes to the water system that we depend on, for example. And basically, with every additional amount of global warming, the changes get larger. So I've heard it described that at 1.5 degrees, a lot of adaptation is still possible. At 2 degrees, it's very difficult and many systems are at risk. And beyond that, we don't have a guarantee of the capacity to cope with or adapt to the kinds of changes that could be driven by that much climate change. So I summarize this. I think the summary for policymakers from Working Group 2, this Adaptations, Impacts, and Vulnerability group, makes for really sobering reading. I summarize it in a Twitter thread with some highlights at the top, and then one tweet per section that puts into plain language what the report says. And I think this is, really one that really stood out to me. Scientists are certain climate change threatens people and life on planet Earth. If humans fail to rapidly reduce emissions, quote, we will miss a brief and rapidly closing window to secure a livable and sustainable future for all. So that's really what is at stake. That's why climate change is bad. It threatens and basically everything that underpins the people and places that we care about around the world. Okay, so we have shown that it's warming, it's us, we're sure, from Working Group 1. It's bad, the focus of Working Group 2. Now let's take a look at Working Group 3 of the Intergovernmental Panel on Climate Change. We can fix it. That's what this third report is about mitigation, so preventing further climate change. And let's look at what that says. One really important conclusion from the IPCC work is that the climate we experience in the future depends on our decisions now. It takes some time to fully experience the effects of decisions. So we basically are living with the climate determined by previous generations. And we are now determining the climate for the rest of our lifetimes, and really the rest of the lifetimes of many, many, many generations to come. Carbon is forever. Some of the carbon that we emit today will still be in the atmosphere, causing warming 10,000 years from now. And that is such an incredible legacy when you consider that, for example, the Great Pyramids or Stonehenge have only been around for about half of that time. You realize that the decisions we make today and how fast we manage to get off of fossil fuels makes this huge, tremendous, incredibly important difference for life on planet Earth for us and for basically every human who will follow us. So we have such an important role to play. We know where climate change comes from. Human activities basically come in two flavors that influence the climate. There's burning fossil fuels like coal, oil, and gas, and you can see how much those have contributed to the increase in carbon in the atmosphere in this graph from the Global Carbon Project. And there's land use change. So that's deforestation and agriculture, raising animals and replacing natural ecosystems with our farmed animals and crops that causes land use emissions. Nature is doing us a huge service by taking up about half of our climate pollution, for our carbon pollution, for free. So from both life on land and in the oceans, taking up about half of the carbons that humans have emitted since 1850. So that's a huge benefit, because we would have way more warming without those services. But we still have gone from about 280 parts per million concentration of CO2 in the atmosphere to 415. Basically, what we have to do to stop climate change is completely stop adding carbon to the atmosphere. We have to leave fossil fuels in the ground, and we have to make a transition to agriculture that works with rather than against nature so that it is sustainable. In more technical terms, to limit global warming, we need strong, rapid, sustained reductions in CO2, methane, and other greenhouse gases. Those are necessary. There's no way to stabilize the climate without making those reductions. Fortunately, there are other benefits to making these reductions. A lot of the pollution that hurts people and kills people around the world comes from burning fossil fuels. About 8 million people a year die from air pollution caused by fossil fuels. So both on a local level, in terms of cities and regions with air quality that's harming people and shortening lives, and on a global level, there are huge benefits to making this transition to a fossil-free world. Well, how are we going to do it? We are not on track to do it yet. Current policies are not compatible with stabilizing the climate. They're not enough. So we need to make more deep, rapid, and sustained emissions reductions than what has been happening historically or what current policies commit us to. You can see roughly in this graph for global greenhouse gas emissions, the red band is essentially current policies, and the light and medium blue bands are policies that are compatible with limiting warming to 1.5 or 2 degrees as promised in the Paris Agreement. So you see there's a big gap between these two, and that's the gap that we need to close really over the coming years and truly months we are down to now. Because if we miss this brief and rapidly closing window, we will not be able to limit warming at a level that can avoid catastrophic climate change. So we're at such a critical time right now. And this is confirmed by the IPCC. Unless there are immediate, rapid, large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 will be beyond reach. So that's what's at stake right now. We have a very small, rapidly dwindling carbon budget to limit emissions within the Paris targets. That's what science tells us. We know that we only have a small amount of tons basically remaining of carbon that we can burn and stay within these limits. So the latest estimate from November 2022 from the Global Carbon Project says that we have about 9 years of remaining carbon budget at today's rates for a 1.5 degree target. In other words, if we don't make any changes, if we stay on from this previous slide in kind of this red band of business as usual, what we're currently promising, we will in 9 years run out of carbon budget and be committed to 1.5 degrees of warming. So that's why we have to make such big, deep, widespread, rapid changes in every sector so fast, because there's so little carbon budget left. This is what that looks like over time to get to net zero, where we're no longer adding carbon to the atmosphere by 2040, if we want to limit warming to 1.5 degrees. We have a little more time if we're willing to accept higher risks and make this transition slower. But basically, no matter what we need is fast, widespread transition off of fossil fuels and to clean energy to stabilize the climate. Fortunately, we know what to do. We know how to do that. We have options in every sector that can substantially reduce emissions, and many of them are already cost competitive. So if you look at the blue bars here, it's actually cheaper to do the things that are better for climate than the fossil or unsustainable alternative already today. And that's quite amazing because actually, there are many political incentives and economic incentives that entrench unsustainable options. So we don't have even a level playing field at the moment. But nonetheless, things like wind and solar have become cost competitive. One of the best opportunities to reduce emissions is avoided demand, basically reducing overconsumption. And you see that, for example, in buildings having efficient lighting and avoid demand for energy services. So basically making sure that everybody's needs are met. We have enough for everyone, for everything, for the resources we have and the carbon budget we have to go around. And we're reducing our demand for unnecessary luxury consumption so that we can replace fossil energy with clean energy as fast as we need to avoid catastrophic climate change. That's a very brief whirlwind tour of some of the highlights of the IPCC, the latest climate science. I go into it in much more depth in my book, Under the Sky We Make, which is structured around it's warming, it's us, we're sure, it's bad, we can fix it. There's a too long didn't read at the end that just gets down to the bullet points of summaries for each chapter. Many people start there, which is great. And I also write a free monthly publication on Substack called We Can Fix It. And that's about evidence-based, actionable advice from a climate scientist on how to face the climate crisis with facts, feelings, and action. So every month there's an update from research or a new study that I break down and describe in terms that are applicable to your everyday life. I talk about linking feelings and facing our climate feelings, because I think a lot of what's stopping us from taking meaningful climate action is anxieties, uncertainties, not being sure what makes a difference, not knowing where to devote our limited time and energy to really have a meaningful impact on climate. And I talk about high impact actions. So what research shows is effective and the best use of your limited time to make a real difference for the climate in your everyday life. So I would love to see you there. That's the best way to reach me at wecanfixit.substack.com. I hope this has been a helpful tour, and thank you so much for learning more about climate. And I'm really glad to welcome you to Team Climate. We need you. Thanks.